So for those of you not familiar with Minibems, just a bit of a summary. We provide heat network performance services, and we enable efficient low carbon heat networks. Our IoT connected devices provide our clients with real-time flow control, automated control strategies, and unparalleled data access. This is backed up with remote monitoring and fault finding for technical and customer support. And with respect to heat pumps, the service that is of most relevance is heat network optimization software that controls flow rates in real time from the heat interface unit through to the energy center. In relation to heat pumps, we can deliver consistently low return temperatures to the heat pump, ensuring high efficiency and better return on investment. And all of this with the goal of delivering more efficient systems, reducing primary fuel energy costs and related carbon emissions, enabling low carbon technologies, and improving reliability and reducing unplanned maintenance. So last week we sort of finished up with Dave Pearson of Star Renewable Energy, looking at a sort of mix of the value adds, the sort of unique value add package that heat pumps deliver, and that's just a sort of wee reminder where we left off last week. So we found that it had a whole series of different things. Obviously, it's low carbon, but also there's the issue with other air emissions locally. It is a local source of renewable energy, so it helps the local economy and also provides energy security. Okay, so today is the second part, and now we're going to be looking at how dynamic flow control can impact on the viability of heat pumps. So we consider how we can deliver different target flow and return to enable heat pumps to deliver low carbon, reliable, and low cost heat. I am going to let Ken pick up the story from here. I shall be on hand to move the slides, Ken, but I'll pass over to you.
Thanks, Ben, and thank you, Finn, for inviting me to speak this morning. The aim today is to emphasise the importance of flow and return temperatures to heating circuits and their impact on the efficiency of heat pumps. This is a more difficult problem for challenging retrofit installations when the heat pump efficiency is dependent upon the quality of the control system deployed. This is a little agenda of what I want to work through. Thanks, Ben. Solid Energy is based in Denmark. I want to start with a quick comparison of the energy sectors in the UK and Denmark. I will then move on to show you our heat pump calculator and how we can use it to demonstrate the importance of flow and return temperatures and to prove that low temperatures generally equal high COP. Lastly, I want to mention our hybrid units for situations when heat pumps don't quite do the job in older UK property. Next slide, please, Ben. This heat loss map of Europe highlights the poor installation of UK housing stock. Denmark has had a focus on heating efficiency since the oil crisis in the 1970s and has a modern, well-insulated housing stock and over 60% on district heating and over 90% in Copenhagen. The poor performance of the UK housing stock should come as no surprise to us. The whole heating philosophy over the last generations has been about letting the buildings cool down overnight, throwing massive amounts of energy in the mornings to bring them back up to temperature, and then to let them cool down again the following evening. For most of my career, I've actually spent on the maintenance of large commercial heating installations, and I don't remember ever having an instruction to improve the efficiency of a heating system. We did specialise in reactive maintenance, and that was very much, there is a problem with the heating. So when we would go to a building, if the boiler was working, we would turn the boiler temperatures up. If the boilers were working efficiently, we would turn the pumps up. So over time, we had a huge amount of inefficiencies thrown in, brought around about by the fact that we were just in poor habits and poorly insulated buildings. Next slide, please, Ben. On this graph, we have the UK barely registered in the use of district heating, with the Scandinavian countries showing us the way. Next slide, please. Modern Danish district energy centres predominantly use heat pumps. Have we gone too far, Ben? That's the one, sorry. And this is a map of Denmark. It happens to show our 3 latest solid energy installations. These are all air source heat pumps with waste capture, and they use either ammonia or hydrocarbon refrigerants. Next slide, please. Next, thank you. This slide shows a photograph of the Ringkøbing Energy Centre, which is our flagship site near to our factory in Stern on the west coast of Jutland. It is a 3.2 megawatt air source heat pump with the evaporators covering approximately the size of a tennis court. You will see there the chimney being from a gas engine in the energy centre, and the town is in the far distance. Next slide, please. This is a 3D of a 5 megawatt air source heat pump now in production. Because with water source, we would only be having the building in the top left, saving the space needed for the evaporators. And now I want to move on to our calculator. If you can move on to the next slide. Clearly, I don't want you to even attempt to be able to read the calculator numbers, but this is just evidence that our calculator is actually a complex spreadsheet, and we can populate the detailed project information provided by our customers to configure the optimum configuration for a heat pump, single or cascaded unit, different refrigerants and pressures to ensure the highest possible COP. The slide actually only shows a small section of the spreadsheet. What we've done here is we've put in the details of a 500 kilowatt water source heat pump, and the only information that we're going to change on the slides is the changing flow and return temperatures, and we're going to keep the temperature of the source water exactly the same. Next slide, please. So here we have a close-up of the 2 graphs that we're going to use from our calculator. The graph on the left has 3 lines. The green is the electrical input, the red being the heat output, and the black is the heat demand of the heating network. The right graph, the blue line is the COP, which will remain consistent at all outside temperatures. And I want to show you the equivalent graphs for an air source pump later on in the presentation. But at the moment, this scenario, the water temperature that we're going to use as our energy source remains at 10 degrees C. And here we have a flow of 85, a return of 75, and a COP of only 2.3, which is not even good enough for RHI. Next slide, please. On this slide, we're using a flow and return of 70-60, and the COP is written to 3. Everything else has stayed the same. Next slide, please. Here we have a further rise of COP to 3.75. The heat pump is becoming more efficient, and the flow and return temperatures here are 60-40. The advantage of having a 60-degree flow, by the way, is that we can now use plastic pipes in our distribution network and the reduced installation costs. I have done a set of 6 calculations to show the good, the bad, and the positive, ugly results, which can be summarized in one graph, which is on the next slide, please. And so here, I just want to emphasize the water temperature is exactly the same. The COP varies from 2.3 to 3.75. And we can have fuel savings up to 38% if we get the control systems correct. This is determined only by the flow temperature and the controls to ensure the lowest return temperatures. Next slide, please. Now here, we've taken the source water temperature up to 20 degrees C. This is at the top range of water available from mine shafts in the UK, by the way. And a 70-40 flow and return generates a COP of 3.64. So we can already see that higher source water temperature can contribute to the higher COP, but this advantage can be lost with high temperatures and low delta T, as is shown on the next slide, please. So here, again, we've got the 85-75, 70-40, 60-40, with a hugely varying COPs. And with the right controls, we can get up to 42% savings. On the next slide, please, we can combine the readings from the calculator, and the summary clearly shows that the high COP numbers are driven by low and return temperatures and not by the temperature of the source water, although obviously this does help. The importance of the design of the heat pump and the maintenance of the return temperature with effective controls cannot be overstated. Next slide, please. Just as a matter of interest, this is the calculator used on an air source heat pump. The COP graph on the right clearly varies with the ambient air temperature. The small drop in the center of the COP line is due to the de-icing cycle that is essential at temperatures below 5 degrees C. Next slide, please. I am often asked, what does a 500 kilowatt heat pump look like? Think of 2 small shipping containers. Maintenance access, by the way, along only one of the sides. Next slide. They are actually not shipping containers. Our designers will be really upset to hear that. They're actually purpose-built modules, and this happens to be a twin compressor LW80 under manufacture in the factory. Next slide. And this is a close-up of a hydrocarbon compressor, which we're using for our smaller heat pumps in the UK, nearly as efficient as ammonia, and with cascade units and advanced controls, and plus the benefits of lower capex and significantly lower maintenance costs. Just to put a number to that, we actually think it is around about £2 per megawatt hour, which when you compare it to other energy sources is significantly cheaper. Next slide, please. When it's not possible to use heat pumps, then a pragmatic alternative is a hybrid, when the boiler can be incorporated into a plug-and-play unit, especially when high flow temperatures are unavoidable. And Solid Energy in the UK have been asked to design a hybrid unit, and I just want to flick through a few slides to show you what they look like. You can put the next one on, please, Ben. So it's going to be introduced into the UK for the retrofit market. In this illustration, the evaporators are on the roof of the unit, the heat pump and the cabinet and the pump cabinets are on the left, the gas boilers to the right, with buffer tanks located centrally. Next slide, please. So here we have the evaporators that can be positioned away from the heat pump unit. This illustration shows two alternatives, either the standard array shown on the left, or in fact a soundproof unit, which is shown on the right of the illustration. Next slide, please. This slide shows an earlier version of the heat pump calculator and how we've used it to help with the design of the hybrid. The green section in the top right-hand graph shows the heat pump covering the base load, with the gas boiler utilised only to cover peak demand, shown in blue. Next slide, please. We've used this graph to report on the carbon savings. The heat pump offers 65% carbon savings against gas now, and with the continuing decarbonisation of the grid, will be about 95% in 2050. Next slide, please. And this really shows that if a heat pump cannot be used, then a hybrid unit can still contribute to carbon savings. With a reduction in capital expenditure of 32%, they can still reduce, with a reduction of capital expenditure of 32%, they can still reduce carbon savings by 15%. The carbon savings produced, if you can show the next slide, please, Ben. The carbon savings produced by heat pumps are not theoretical. This app shows the carbon equivalent of a gas boiler and a ground source heat pump. That heat pump shows 0.68 grams of carbon dioxide per kilowatt hour compared to a gas boiler at 215. And this is dated the 30th of September 2019, not unusual numbers. But interestingly enough, at 10 o'clock on the 19th of April, when this presentation was being prepared, the 68 figure was actually down to 16, which is a staggering number, but becoming more and more usual. This app, by the way, is available on the Ground Source Heat Pump Association website, readily available, and is of great interest. So thanks, Ben. Happy to take any questions.
Brilliant. Thanks very much, Ken. There was quite a lot in there, actually. So yes, if you've got any questions, those of you attending, please pop them in the question box. They should be on your right-hand side. I think we're going to sort of kick off with perhaps just delving into the impact of real-time flow and what the sort of Minibems approach to that is. Would you be able to perhaps give the Minibems side to that, to what Ken's been presenting, Finn?
Yeah. So as you've nicely demonstrated, Ken, there's a very significant energy saving from moving from higher flow temperatures, higher network flow temperatures to reduced flow temperatures. I thought what was interesting, actually, from your COP summarized table that you had there, you're quite quick on some of those slides, but I think I understood that even a 10-degree change in water temperature, where using a water source heat pump had very marginal impact compared to actually reducing the control temperatures of the heat network. Was that right?
Absolutely. Yeah.
Yeah.
That's right.
So,
I'm sorry if I was a bit quick on the slides. Perhaps everybody can dwell on them at leisure later on. But no, the the impact of the water source is far, far less important than the flow and particularly the return temperatures on the efficiency of the heat pump.
Yeah, okay.
When I was putting together those calculations, it staggered me. I didn't realise actually how much the impact was from the flow and return temperatures.
Yeah, no, it was certainly interesting. I certainly thought that the energy source would have more of an impact than control temperatures, but no, it clearly shows that your control temperatures are much more critical in your heat pumps. Yeah, okay. So yeah, so to answer the question with Minibems then, how do we achieve that kind of 60-40 paradigm? I mean, you can see here on the slide that Ben's put up here. This is a block of 25 flats running over a 4-day period, and you can see the blue and the green lines are showing all the load variations over that 4-day period. What you can also see is that the return temperature is relatively consistently held at 40 degrees, and that's because the HIU downstream of that block meter data that you're seeing there is optimizing the heat transfer performance in every single HIU, so that you've got this low return temperature of 40 degrees coming back. But the other thing that we're doing, as well as managing delta T on the HIU, essentially, what we're also doing is each Minibems controller is calculating a real-time flow temperature requirement and sending that back to the energy center, so the energy center can blend the real-time flow temperature that's required to heat those apartments. Now, what we know from years of data is that most radiator systems, even your old sort of 82, 71 radiator systems that were fitted a long time ago, can be run at, believe it or not, 55, 35 or 60, 40 for a lot of the year and still heat the heat properties sufficiently. I think we probably all know that radiator sizing back in 20 years ago was not exactly a fine art, and there's a lot of opportunities for optimization of radiator temperatures according to actual real-time demand. So that's what really allows us to get the control temperature down. It's just compensating down that radiator emitter flow temperature according to real-time demand. I mean, you're obviously very suited to your hybrid unit where you can deliver both low temperature and high temperatures over the year. Yeah, does that answer the question?
Listen, I think we've got further questions that sort of link into that as well, Finn. But no, I thought certainly that's great summary there. So I've got a number of questions coming through. One is from David Telford. Thanks, David. So he asks, when doing a carbon saving calculation, do you use average grid intensity or the half-hourly regional figures now being used by National Grid? When using the opportunity to decouple power use from heat demand, this gives a much more significant carbon saving. So I guess it's using the real intensity of the grid rather than an average.
What we found actually, Ben, is that the numbers that we are obliged to use when calculating COPs and carbon savings are ones that we have to use to fit into the standard regulations. When we look at the carbon savings in particular, though, the reality is much better than the numbers that we're using. The regulating bodies don't seem to be keeping up speed with progress in the decarbonisation of the grid, and so calculations today actually should demonstrate greater carbon savings, but we're not always allowed to use those figures because building regulations actually state what the carbon content of the grid was 3 or 4 years back, not now.
Nice one, nice one. Just a couple more points. Paul Noonan, thanks for getting in touch, mentions the benefit of using large air source heat pumps in heat networks with a genuine summer heat load, domestic hot water or process, a higher overall COP can be achieved due to the warmer air temperatures with small summer loads. He asked the question, is anyone using this summer advantage of air source heat pump? And
yeah, that's a good point. Obviously, in summer, I mean, a lot of heat networks in reality are about 40% efficient. I mean, Ben and I have surveyed a lot that have been a lot worse than that, sort of down at the 25-30% end. And if you think about that being the overall annual performance, your summer performance is really terrible. You know, your summer heat network performance can be down as low as 10 to 20% of the gas input that's going into that network is transferred into actual utilized hot water. Yeah, it's a very good point that, you know, in summer, if you're running an air source heat pump, you're going to get a much better COP, aren't you, Ken, than over the course of the winter. And, you know, your carbon intensity, therefore, of generating that hot water is going to be much lower.
The solid energy heat pumps, they're all inverter driven, and we can modulate down in the summer to 50% before we lose efficiencies, which is, it doesn't sound a good number, but actually for heat pump design, that's it's a tricky number to achieve. But we've actually got down to 50% before we have any impact on the COP.
Yeah, obviously you'd need some decent thermal storage to go with that then, essentially.
Well, I was going to say thermal storage is a topic we haven't covered.
Yeah.
But that's so important in the operation of the heat pump, to limit the on-offs to a sensible number, and to just provide that thermal storage to just smooth out all the curves. Again, is so useful.
On your hybrid units, Ken, what capacities are those? What outputs are those?
At the moment, as the drawing showed, there's still sort of a design stage for the UK. But we're going to stick to 250 kilowatt, 500 kilowatt, and 800 kilowatt outputs, on any combination of those. We don't see these going over 1 megawatt.
Yes. Okay. Yeah. Okay. And the COP table that you showed earlier for those units, what was the assumption on the percentage of heat pump usage versus boiler usage?
The assumption is 85% heat pump usage and 15% usage on the boilers.
Yeah.
In fact, we've done some calculations to show that in one instance, a gas boiler will be running for less than 100 hours a year to cover peak loads. So the 15% is a very conservative number.
And have you done that using sort of degree day data and therefore working out what the flow temperature of the network's going to need to be? Yeah. Okay.
Moving on to next week, we'll be looking at what is missing from the Scottish Heat Networks bill. The consultation period is coming up on the 15th of May. So we are going to run a sort of one-off panel discussion next week. Same mornings, Tuesday, Thursday mornings, looking at we've got Sarah Jane coming from Brodie's, who's looking into this, and will be able to share some thoughts in terms of what may be required to really deliver. And we believe it may be of interest to people beyond the Scottish geography, as it probably has some pointers in terms of what's coming down the line across the UK as well.